Again, thank you so much, everyone, for coming, for joining us today in this webinar. So for today's webinar, it is all about could the Francis Scott Key Bridge have been saved? So this is actually a technical webinar which will be presented to us by Dr. Igor Shafrin. He is actually one of our EIT lecturer and course coordinator in civil engineering. Okay. All right, so for some of our common questions and frequently asked questions, so basically everyone who have registered to our webinar today will receive a PDF file and a video to your registered email within the next 2 days. All right, so kindly monitor your junk mails or spam messages. It might go straight there. So, yep, and then since this is a technical webinar, we will be providing a digital certificate of attendance to our live attendees for today. Okay, so I will be providing a link or QR code and instructions after the presentation. So you may need to request this one before you'll be able to get the certificate, and it will be delivered to you in the next 4 business days. Okay. All right, so for everyone who is new with EIT, I would be sharing with you information about EIT, who we are, what we do. So basically, EIT is an education provider which ensures that our students receive a world-class education and gain skills that can immediately implement in the workforce. So we call ourselves as an engineering specialist because we're the only one. We're actually one of the world who is offering engineer specializing in engineering courses. So we offer wide variety of courses, starting from professional certificates, diplomas, advanced diplomas, undergraduate and graduate certificates. We have bachelor's, master degrees, and Doctor of Engineering. So these programs are actually industry-oriented programs, which are designed by industry experts to ensure that our graduates have the cutting-edge skills that can be useful in the industry. So our programs remains current with the rapidly changing technology and industry developments. So our programs as well has a world-class Australia accredited accreditation. So our vocational programs and higher education degrees are registered by the Australian government, as well as we have programs that are recognized under the three international engineering accords. So these programs are delivered by our industry experienced lecturers. They are highly experienced in the field, and they are specialists with knowledge that can be useful to our students when they are actually learning from us. So the technologies employed by EIT, both online and on campus, enables our lecturers from a large global pool of expertise. So we deliver our programs via a unique delivery methodology. Okay, we use of live and interactive webinars, as well as I mentioned earlier, international pool of expert lecturers, and we also have our dedicated learning support officers and state-of-the-art hands-on workshops, remote laboratories, and simulations. Okay, so for today's agenda, as you can see on your screen, this will be discussed by our presenter today. But please remember at the end of the presentation, there will be a short Q&A wherein you can actually drop, share your, if you have any questions about the presentation about the topic. So you can drop them down on the message in the chat box, and we will be happy to answer them for you. Okay. So about the presenter, um, this is our presenter is Dr. Igor Shofrin. So I would like Dr. Igor to introduce himself for this particular topic, and then yep, Dr. Igor, the floor is yours.
All
Thank you.
right. Okay, thank you for the introduction. Let me just get my screen. Okay, that will be at my screen. Right. Thank you for the introduction, Lauren. As the As Marvin said, I'm a course coordinator in structural engineering and civil engineering at AIT. I've been an active researcher for over 30 years. I've published over 30 papers and co-author of some handbooks in civil engineering. And for bridge engineering, I've been teaching this unit in AIT for a couple of years already. So, right, I apologize that you cannot see me. For some reason, you can see, well, I've mentioned I'm been trained as a structural engineer, not as the IT manager. So, for some strange reasons, my camera doesn't want to turn on. I have two actually here around me.
Right.
I cannot turn it on. Right, that's the introduction. Let's get started. Let's get moving into the presentation itself. Just few last touches. I can see I can use the highlighter. Right, be able to use the highlighter. Right, so the main goal of this webinar is to draw your attention to protection for bridge superstructure. So we will use the example of Francis Scott Key Bridge Collapse to discuss the danger of progressive collapse type of failure. We will then discuss ASHTA provisions for vessel collision, and we will look at the risk analysis and impact load assessment. Right. We will survey ways the bridge substructures can be protected. Right. And we will finish up answering the question if the Francis Scott Key Bridge could have been saved. Right. So, as the disaster happened on March 26 this year, 6 weeks ago, at about 1:30 a.m. local time, a container ship hit one of the pillars of Francis Scott Key Bridge. The bridge of an overall length 1.6 miles that is crossing the Patapsco River in Baltimore. This collapse caused 9 construction workers and 3 vehicles to fall into the water. Unfortunately, 6 people were reported missing, out of which 3 bodies were recovered and the other 3 are presumed dead. 2 people were rescued from the river. One had no injuries, while the other one had to be taken to the hospital, and he survived the disaster. For the structural collapse, all 3 main steel truss spans collapsed together with 3 approach girder spans on the northern side. Right. I'm trying to follow. Probably I will not follow the chat box because it's a little bit too hectic. So I will answer the questions at the end, and the administrative questions Marvin will answer probably on the way. So the ship that struck the bridge, right? The ship that struck the bridge. Where's this? Yeah, right. The ship which they called MV Dali was a Singapore-listed container ship with an overall length of 300 meters and a deadweight tonnage of over 116,000 tons. Right? And it was loaded, so the overall weight of the ship at the collision was much higher. The steel truss fell on the ship bow, you see in this picture, and the fire broke out on the ship, but it was extinguished later without major damage. So the bridge collapse blocked most shipping to and from the port of Baltimore for a few weeks. On top of this, the traffic needed to use alternative ways. Now, the Francis Scott Key Bridge was a steel arch continuous through truss bridge that spanned the lower part of Patapsco River and an outer Baltimore Harbor. The Key Bridge was named after the author of U.S. national anthem, Francis Scott Key, who was believed to be near the site of the future bridge in this time. He was there in 1814, and he served there in the army. And when observing the bombardment of Fort McHenry nearby, he wrote a poem. But this battle inspired him to write a poem called "The Defense of Fort McHenry," so like Henry Fort. Which this poem later was set to music and renamed the Star Spangled Banner, which is the national US anthem at the moment. Right, so the construction of the bridge started in 1970 and was completed in March 1977, so about 5 years. So this is an important data for this is an important date for our discussion, right? As the federal regulations for protecting bridges from ship collisions were updated in 1991 after another truss bridge, Sunshine Skyway Bridge collapsed in 1980. The existing bridges in 1991 actually were exempt by a so-called grandfather clause. And this grandfather clause allows for the old rules to continue, and it applies only for some existing cases, and the new rule will apply for all future cases. When the new regulations came in, they were overshadowed by this grandfather clause. So as a result, the Key Bridge, this bridge, was essentially lacked the level of fender system or island barriers required by the standard for the newer bridges. After the bridge was open to public, it underwent some renovations several times, including one of the projects is in 1986. They repair some damages, improve safety, to restore the bridge appearance, and so on. To the best of my knowledge, the bridge was determined as fully compliant with the building code when it collapsed. So, a bit more details on its structural arrangement. The bridge itself spans 1.6 miles, so which is about 2.6 kilometers. It's over the river, but the crossing overall structure, including its connecting approaches, is almost 14 kilometers long. So the steel truss section was 805 millimeters, with the maximum clearance 56.4 meters, with the longest span was 366 meters. It was a very busy bridge, transferring according to the Maryland state government report, by average 11.5 million vehicles, and only in 2023 the report states 12.4 million vehicles crossed the bridge. So whatever the Francis Scott Bridge could have been saved is a complex question with no definitive answer. There are ongoing debates among experts. Here is what we know. The bridge had a fendering system, right? designed to absorb impacts, but the severity of the collision might have been overwhelmed. So some engineers believe stronger defensive measures like improved fendering system could have lessened the damage. Others argue that the force of the colliding ship might have been too great for any current technology to fully prevent the collapse. Now, officials are still investigating the incident, so a clear picture may emerge in the future. The bridge's continuous truss is known to be sensitive to the progressive collapse type of failure. And as such, this type of truss has no redundancy against removal of any part of it, in particular, one of the supports. So let's just examine what happened there. I cannot turn, I just need to turn this video. Why I cannot do this? Yeah. Right. So at the moment, all information we have is the video footage of the collapse. And this, however, fits the concept of progressive collapse clearly. So you've seen this video footage, many of different footage, the videos released over the internet. It's the main one. Right. So let's restore the chain of the events. I will use this schematic representation to follow the collapse stages through. Now that's my bridge with the main truss, main dimensions for the truss part. Right, so this structural form is a combination of an arc bridge and a suspension bridge. The continuous arc structure, that's a truss structure here and about the supports, provides the horizontal thrust for the arc structure. This is my arc here. And it's designed to reduce the thrust as well. So instead of an arc supporting the structure from below, the arc here, you can see these parts, rises above the road, and the vertical ties descend to increase support of the decking. Well, it's extremely strong arrangement because the arc design allows the forces from the deck to go to arcs where hangers here, you see the hangers, which means no part of the bridge takes on the high amount of pressure and as a result is not designed to it. So we see here the trade-off, which will be advantages which turned out to be the disadvantages in terms of the progressive collapse issue. So what happened? The cargo ship loses control and collides with the southern pier. Though the ship wasn't built for speed, it was going relatively fast, actually 8 knots, which is about 9 miles per hour, which doesn't sound like a lot to most people, but with the weight over 100 and probably 50,000 tons, even at 8 knots, the sheer mass of the Dali meant that it threw a massive amount of force against the bridge support. The bridge support is a structure that was primarily designed to withstand downward forces, not sideways forces. Right? So under this collision force, the piers is the collapsing, essentially was completely removed. The southern truss, this is south, this is south, and this is north. So the southern truss buckles and fails. The whole truss moves sideways due to this. It all happens in a matter of instants, fractions of the seconds. The northern end lifts of the pier, not connected to the pier anymore. And it all rotates over the support. The support then is a pivot, so it actually exerts additional force on the pillar. The members of the truss now experience forces that exceeding the design capacity and fail while the whole truss is already in the air. So next moment, the southern truss collapses under the sideway force and it falls into the river. So the middle span not supported anymore, and there's no left support, so it becomes a cantilever end, and it breaks at the top core here. Well, you can clearly see the structural arrangement is changing. So this truss was not built at the top core to withstand this these tensile stresses at all. Well, the middle span then snaps, and it immediately snaps near the northern pier, this one. And the top core breaks, and all this fall into the water. The remaining sections of the northern truss pivots backwards, causing the failure of the approaching girder spans, so causing the failure of these parts. The three northern girders also collapsed into the water, and that's what we see at the end. So, as you've seen in the video, all this story took less than a minute time. And that's the essence of the progressive collapse, and that's the problem of the truss bridges, especially the problem of the continuous truss bridges. However, it wasn't the first time this type of bridge and this type of failure occurred in the US, because in May 1980, a freighter ship ran into one of the bridge piers of the Sunshine Skyway Bridge, as Tampa Bay, Florida. Here on the picture, before, after. The bridge was very much similar dimensions, actually, 366 meters, and the height was similar, and it was more disastrous. 35 people were killed in this disaster. Even more recently, after this, a couple of cases in 2013, just 10 years back, a freight truck, struck the overhead structure of the Skygate River Bridge. So it is a truss bridge in Washington state, causing this partially collapsing, but extraordinary killing no one there. So all this, as we see, right, wasn't really new for civil engineers or bridge engineers. The Sunshine Sky Bridge was rebuilt, but using different structural forms. So it's the cable, that's the new bridge. They're using cable stayed structural form. Couple of reasons. It is the main one. It provides higher redundancy levels and provides the longer clear spans. In response to the Sunshine Skyway Bridge Collapse, AASHTO sets new standards for highway design and construction in US, and it addressed vessel collision with support piers. And that's what we want to look at. Next, a couple and explain. And that's what I want to now to show you how ASHTO sets out the recommendations for the modern design and of bridges for vessel collision. So that's what it says. In navigable waterways where a vessel collision is anticipated, structures shall be designed to resist these collision forces. Right. The vulnerability of a bridge to vessel collision is affected by a number of factors, including the waterway geometry, water stage fluctuations, water speeds, weather conditions. Also, we will need to include the vessel characteristics, navigation conditions, the vessel size, speed, loading conditions, and the bridge. On the third parameter here will be the bridge size, bridge location, so where it sits, horizontal vertical geometry, structural redundancy, as we mentioned already, and effectiveness of existing bridge protection system. Right? So what's important for us to understand that vessel collisions with bridges are extreme events. It's a type of extreme event which associated with the great amount of uncertainty, well, especially with respect to the impact loads involved. And as uh, as the other types of extreme events, it will be too conservative and not economical to design the bridge for the worst case scenario. That means that a certain amount of risk must be considered as acceptable. The design objectives in this case is to minimize in a cost-effective manner the risk of catastrophic failure of a bridge. So reduce the risks of vessel damage as well, and environmental aspects should be taken into account as well. Right. So in navigable waterway areas where collisions of the vessels is more likely, so bridge structures should be designed to prevent collapse of superstructure. So we need to consider all these aspects we mentioned earlier, so size and type of vessels, available water depths, vessel speeds, structural response. So all this needs to be included into the risk assessment. So it should be presented in a way of reliability, so probability of the events. ASHTO provides three alternative design methodologies, so method 1, 2, and 3. One is relatively simple, semi-deterministic procedure. So for selecting the design vessels and computing the collision impact loads. It is particularly useful for shallow river waterways, with where the vehicles are and the barges or vessels are to approximately the same size, so the forces can be easily estimated in more accurate way. So method 2 is a probability-based risk analysis. So this procedure can be used for directly assessing the risk of collapse from vessel impacts and developing vessel impact criteria for the design. So in method 2 procedures, the mathematical model is developed to estimate the annual frequencies of bridge collapse. So probability of accidents of this risk will lead us to the predetermined acceptance criteria. Right. Method 3 is the cost effectiveness procedure, where the benefit cost analysis is combined with the risk of a potential bridge collapse to determine the applicable design vessels here. So method 2 is the preferred procedure, which we will discuss next. Right. In general, the occurrence of collision is separated into 4 events. A vessel approaching the bridge becomes aberrant. The aberrant vessel impacts a bridge element. 2. The 3 will be the bridge element that it hits fails. And 4, the protection factor based on bridge location and nearby waterways features. So the AASHTO risk equation shown here provides the annual frequencies of collapse for single bridge elements in terms of these factors. So PAF, the protection factor, accounting for land masses or nearby structures that may be able to protect the bridge. PC is the probability of collapse, providing the probability of collapse for the whole bridge if a bridge component is hit by an aberrant vessel. PG is the geometric probability, is the probability that an aberrant vessel will hit a part of the bridge. The next one is the PA, probability of aberrance, is the measure of how often a vessel might go off course. The last one is the annual number of vessel trips classified by type, size, and loading conditions that use this particular water channel, and they're able to strike the bridge element. So once all this input information for the analysis has been collected and developed, the previous coefficients, and usually the most time-consuming part of the process to collect all this the information required to calculate these factors. So then the risk evaluation can be made up by summing these factors, right? These analysis factors for each bridge component, for each vessel separately, and transit path in the analysis is formed. So what you see here, the example of these tables, there are some software available as well to deal with this. So what you see is actually for all these factors, so we mentioned NPA, PG, PC, PF, growth factor, they are done for all outbound, inbound vessels, for all different vessel types, which we'll discuss shortly how we define them. So for all this done for each structural element, for example, Pier 1, Pier 2, so on, abutment, so it's all we define it. So we sum all this up at the end. Once all, right. So the inverse of the annual frequency of the collapse then represents the return period in years of the failure event. So that's the one we obtained in the previous calculations, right? SAF. Sorry, just one moment, please. Let's go back here. Right. Sorry. I just needed a drink. So, right. Just go back for a second. Once we calculated all annual frequencies of bridge component for all conditions, right? I'm just repeating this part. We're summing them up, and we obtain the annual frequency for overall bridge. So this frequency, this AF, if we inverse this annual frequency of collapse, we will get the return period in years of the failure event. So similar approach for risk assessment is used in other areas of structural engineering in terms of the extreme events, earthquake engineering, blast, the protection for the blast loads, and so on. So ASHTA provisions specify the annual frequency of collapse here, the 0.001, for critical bridges. So an annual frequency of collapse only 2.001 for regular bridges. So critical bridges are defined as those bridges that are expected to continue to function after the major impact due to importance level. So there's the same idea of importance importance levels popping up here as well. So we've seen this in different areas of structural engineering as well. All right. So these annual frequencies will correspond. So this and this will correspond to 1 in 10,000 years. This one 1 to 10,000 years. This one is 1 to 1,000 years, respectively. Well, obviously, this does not imply that the structure is expected to last 10,000 or 1,000 years, right? But that during this nominal design life of the bridge, say 100 years, the risk of collapse due to collision by a vessel in the design fleet will be very small. That's the idea of this. Right. So the number of vessels, and so we haven't discussed this one yet, and I just want to go through all these factors briefly to show how we calculate them. So we'll start from the number of vessels that could potentially strike a bridge element. So it's based on available water depth and actual draft of the aberrant vessel. So again, we need to specify a number of possible vessels there, which should be assessed based on the current conditions there. This risk assessment must also include the effect of the vessel's ballasted and loaded vessels. So what's the difference? So loaded ship profile, you can see here the ballasted ship profile on the way back when it's actually a load is low, they must carry some ballast in order to keep the ship under the bow line. So in certain conditions, you can clearly see here that the slope of a keel is changing. So this needs to be taken into account as well. Right. So we need to remember that physical ability of a vessel to strike a bridge pier is based on available water depth at the location of the pier and the draft of the vessel. So essentially this. So if the draft is not sufficient enough, so for example, loaded ship with a 10-meter draft would run the ground before it could strike a pier in 6 meters depth of water. Although the same, at the same time, so the same ship when it's ballasted, not loaded, will be able to reach this because this 2.5 meter draft, which will be the lower, and the vessel will be able to reach the pier in this case. Well, usually when we deal with this, so we need to acquire the data at the particular location. So the vessel fleet transiting this navigation channel subdivided into 2 categories. So usually in increments of thousand. The DWT is the dead weight tonnage. Uh, and they will have all these different types of vessels in our tables in order to estimate the total risk of this. Right. The probability of aberrance, PA, just let's go quickly through these different factors to understand what they mean. We don't have much time left, huh? We waste too much time at the beginning, right? The probability of aberrance is a measure of risk that a vessel is in trouble and may stay off course as a result of pilot error, adverse environmental circumstances, mechanical failure, whatever happened to this MV Dali in our example. So Ashta offers the following approximate method here. So all these factors. So to calculate this PA, we have the different number of different factors which can be found in the which we will look at this. So probability overall, the BR aberrancy base rate based on historical accidental data of waterways. The RB correction factor for bridge locations is computed based on the relative location of the bridge to one of the three waterways regions. So we've got straight, transition, and torn bend. So depending where the bridge are on the waterway. So this RB will take different values. So on geometry of the tunnel and the position of the bridge on this tunnel. Next one is the correction factors. So correction factors for currents acting so parallel or perpendicular to currents. So on the way the bridge is set and the water currents there. So in this case, you also have the ways to calculate this RC, this factor, taking into account current velocity components and so on. So all this is described in ASHTO in the standard. So I will probably rush through this. So bridges, well, the main idea when we look at this expression is that bridges should be designed to cross the navigation channels at right angles, right? And better be symmetrical with respect to these channels. Next one is the probability of aberrance. This one is RD, the correction factor for vessel traffic density. So in the immediate vicinity of the bridge is determined by whatever structure is located in low, medium, or high density area. So for this, we use the geometric probability. So you can see these schematics here, right? And this probability that a vessel will hit a pier if it has lost control near the bridge. And we can see how this all this geometric probability set, right? And we will position this in respect with the width of the channel, the central line of the pier. So this will give me this geometric probability once we set it on. The probability of the bridge collapse, the next one, and when the aberrant vessel strikes a pier is a function of vessel size, type, bow shape, and so on, right? So with this is done. Just a second, give it a PG, right? Just 1 second. Right. Okay, that's the PC. Now we need the next one is a protection factor. So next one is a protection factor, PF. The protection factor is used actually to adjust the annual frequency, the AF, for full or partial protection of the bridge piers on its spans components. Well, it is taken regardless of actual water depth, and that's where we're taking into account the protection measures or some shielding associated with the existing some existing conditions. For example, it's the protection measures which we will have a look shortly, or some existing upstream or downstream the natural protection, such as a shoreline or peninsula extending out. So it all provides the natural protection in addition to the artificial protection which we want to provide. So all this protection factor is actually calculated for all different means of protection, right? And then it's also evaluated as the probability distribution in this case, right? Right. Yeah. So then next step is to estimate the impact loads. So it's the impact loads on the bridge pier during a ship collision. Again, it's a very complex problem. That's actual force depends on time, the ship collision forces. But we commonly do, as in structural engineering, we use equivalent static forces in this case. And how we apply them, to apply them statically. So we need to know two things. We will start from the vessel collision energy. So the vessel collision energy, which is the kinetic energy of a moving vessel, and this energy to be absorbed during the collision with the bridge pier or with the protection system. So, and this is the vessel collision energy here. That's the expression. We have the CH is a hydrodynamic mass coefficient. V is the impact velocity of the vessel, and W is the displacement tonnage. So pretty straightforward, adjusted by these coefficients as well. So the hydrodynamic mass coefficient is taking here as the proportion as increasing actually the vessel displacement tonnage, W in this case. Right. Next one is to calculate the head-on ship collision impact force on the pier. So the ASHTA provision uses this formula to calculate this force to estimate this static equivalent impact force. Right, so we've got here two parameters actually: the vessel impact velocity and the deadweight tonnage of vessel (DWT), which we've seen earlier. So, for example, how it's done. So the typical impact forces are shown in this diagram, so they correlated through this equation. So let us now estimate the impact force experienced by the pier of the key bridge. Right? So the speed at the impact we said was 8 knots. So deadweight tonnage, well, we'll say so 116,000 tons. So the impact force here, so I'll go on this diagram. I will find it in KIPS on this diagram, or I can calculate it here. So it will be using this expression. Actually, we'll find it. The KIP, it's the British, the imperial units, but when we look convert this into kilonewtons, we will have this enormous force of 166,000 kilonewtons. So 166 meganewton. That was the force experienced by the pier in this collision. So there's formulas for computing the design ship collisions for lots of different situations. I can see for some different reasons we're running very much out of time, and so we'll probably skip a couple of slides. So the impact loads for different type of loads. So we got ship bow impact force, we have deck house impact force, so-called ship mast impact force. So all that's the expressions that can be found in ASHTO. Right, that's all. There's different cases, different scenarios of the collision, the ship pier collisions, right, and applications of this impact force, right. In this case, the first one applies the concentrated load at the bottom of the pier, and I think that's the same slide actually. And then there's another way is for local collision forces to be estimated. So this impact force is applied as a vertical line, so equally distributed along the ship bow and the depth for the ship. So we have two different distributions here. That's another way to apply these forces. Right, that's the estimation of forces. Another part I wanted to show you is the protection of the bridges, so protection of substructures. So piers exposed to vessel collisions can be protected. All these special structures designed to absorb the impact loads or redirect the aberrant vessels away from the pier. So called deflection walls. The same idea is actually used for the bridges, for road bridges, or railway bridges as well. So for the road bridges, it's called deflection walls. So the large forces and energies are involved in this vessel collision. So protection structures designed for plastic deformations and to dissipate these energies. So general types of physical protection include fender systems, pile supported structures, or dolphin protection system as well, they call it, and island protection systems, and as well as the floating protection system. So the first one here is the fender system, usually consists of the timber, rubber, steel, or concrete elements. So you see them here and here, and they built or designed to fully or partially absorb this impact load. The load and energy absorbing characteristics of this system is relatively low. The next one is a pile supported system. So it's a pile supported system. This usually consists of group of piles. They're connected or not connected by rigid caps. Sometimes yes, in this case connected, in this case not. And they set around the piers. This fender system may be attached to the pile structure or help resist a portion of the impact load as well. So it can be attached to the pier, can be freestanding. Right. Dolphins, what's the dolphins? The name is interesting. So we can see the Sunshine Skyway Bridge had dolphins there actually. Oh. So the dolphin protection system usually consists of a large diameter circular cell, you see them here or here on the structure, constructed or driven steel sheet piles down there, right over here. And it's all filled with rock or sand and topped by a thick concrete cap. So vessel collision loads are absorbed by rotation and lateral deformations of these cells. Two more systems here, and they called island protection systems. This usually consists of the island, especially built of a sand or quarry rock, and they protected by outer layers of heavy rock riprap for wave, current, and ice protection. This island geometry is developed to stop the aberrant vessel from hitting a pier. Another system is a floating protection system, so usually consists of cable net systems suspended across the waterway to engage and capture the bow of an aberrant vessel or floating pontoons anchored to the front of the pier. So this floating protection system have actually a number of serious drawbacks and usually only considered for extremely deep water situations where the other protection options are not really practicable. That's the protection structures here. Now, well, coming to the main question we started. So could the bridge have been saved? So this is the statement from the American Society of Civil Engineering. So it states that SCE mourns the collapse of Baltimore Francis Scott Bridge and expresses its support for those affected. And the Society of Civil Engineers is committed to preventing similar tragedies and is developing an action plan to improve bridge safety. That's what it states here. And they also say they will participate in investigation of this. Obviously, some lessons will be learned. Some changes to the provisions will be made. If my personal answer to this question, could this bridge, could Francis Scott Key Bridge have been saved, I will answer no. This type of a bridge, this particular type of a bridge, especially then subjected to such an enormous impact force, could not have been saved. The bridge type and bridge protection system should be considered during the initial planning. So rather than protecting from the coming disaster, we need to foresee this. So this initial planning, the type of the bridge, and its location, and the protective system, they were not planned properly there. Probably for that time, it was okay. So as we have seen from this current risk assessment procedure that we went through, the size of the vessels passing the Patapsco River and out in this Baltimore harbor requires different approaches. So the easiest one would probably be increasing the free span of this bridge, which will eliminate piers in the navigable passage. So it will completely eliminate this risk of collision. So I think the future bridge there will be cable suspension bridge, or again cable stayed bridge, which actually allows very long spans of bridges. Right. Yeah, well, that's these references I've used in this presentation. The main one is Ashto, and plus some other references as well. Thank you. Sorry for being a little bit late at the beginning. Yeah. Thank you for listening.
Thank you so much, Dr. Shofin. Thank you so much for that very informative sessions today. It's very helpful to understand about what happened. And so, yep, after this, we'll be having a short session, a Q&A. You can send all your questions on the chat box, and then Dr. Igor and I will be answering all of them. But before that, okay, Dr. Igor, I just want to share my screen,
Yeah. Yeah,
my phone
sure.
screen. Mhm.
Right.
Mhm.
I can start answering somehow.
Yeah.
So obviously, Richard,
So yes, please.
yes,
Yes.
yes, yes. It is the well, the risk assessment. Risk assessment. Uh, any design decision should be based on risk assessment. So in some cases, additional protection should be implemented, and it will solve the problem. In some cases, you still will not reach the adequate level of protection, so the risk still will be high. Uh, and so if the risks are high, so you just need to go and probably pick different structural system for the bridge. That's that's I believe the main point of this risk assessment procedure.
Mhm.
Any penalties to the implementing authorities? So I'm not sure. Not sure about the penalties.
Mhm.
But the bridge should be compliant, so you will not get approval for the structure
Mhm.
if it's not compliant with the current standards. So
Mhm.
the problem is that the existing structures they they are not compliant with the current standards. And it's a known problem not only in US but in Australia as well. It's a known problem. That's the demand on bridges increased from all perspectives, from the load they need to carry, from the risk, from the collision which we mentioned here. So most of the standards they do implement this what they call grandfather rule. It's not applied retroactively on existing structures, and don't even require from the authority to provide the increased protection required under the current circumstances, right? That's a known problem which we are constantly trying to solve in different ways to introduce retrofit, introduce the protection system, and so on. What else? The questions? Could remember the kind of bridge. Probably to find the beginning of this question. I couldn't look at the chat box during the talk because, yeah, apparently it was a little bit too intensive.
Yeah, we have a question from Isaac Foka. Could remember the kind of bridge.
Yeah, that's what I'm saying. It should be some. I'm looking for the beginning of this question.
Yeah.
It should probably be somewhere. Uh,
So, all right. While Dr. Shofin is answering your questions, I would just like to have this information that this topic is actually covered by these following courses. So EIT is offering these courses on your screen. Okay. And then, yep, these are the courses, upcoming courses that we have. So you might want to check it out. We have the 24th of June, 2024 for the Graduate Diploma of Engineering, Civil and Structural. Okay, so for more information about this course, you may reach to us in our you can give us a call or send us an email or visit our website, and I will be sharing the link here in the chat box so that you can actually check the courses. Okay. And then for our upcoming webinars, we still have 2 upcoming webinars this month. So we have the 15th of May and 23rd of May. Oh, sorry, 29th of May as well.
Right, Marlon, there's a question I can see how where the presentation slides will be available.
Oh, yep. So again, as mentioned earlier, all the registrants, I mean all those who registered, will receive a PDF file and a video after 2 business days, all right, to your registered email. However, for the certificate of attendance, so basically you need to fill out the form using the QR code in your screen or the link which I will be sharing on the chat box later on. You need to fill out that form for request of your certificate of attendance. Okay. And then kindly note that this will be closed on the 13th of May. So after that, we will not be able to issue your request. Okay. So I'll be putting in the chat
Right,
box.
right, yeah,
So
sure.
if you have your phone, you
The
can actually scan the QR code and fill up the form. All right. Yeah, we
right,
have a
I'm
question
not
here, Dr. Igor.
okay. So yeah, I'm not sure. I'm not sure which Tasmanian bridge you mentioned. So
Mm-hmm,
no, I can't answer. I don't know which one is this.
mm-hmm,
Fortunately, well, cannot. No, so I'm sorry, I
mm-hmm.
don't know what it is.
So we have.
So, do we need to consider water? The other question is, do we need to consider water trust before designing? Oh, yes, definitely. It sits on the, when you go back to the presentation at some point,
Mhm,
you will find this water trust sitting in the coefficient. Let me check for you exactly to tell you.
mhm.
So it will be the water thrust sits in the one of the coefficients.
You can share your screen, Doctor.
I can share my screen back, right?
Mm-hmm.
Yeah, I'll take a bit longer. Just give me a second. And, yeah, it is in the RC in the correction factor for currents, right? So it is in RC. I can share it back if you
Mm-hmm.
like, but you don't need yours anymore, right?
Mm-hmm.
That's my sharing stuff. Share. No. Right. So it will be the currents taking into account here. Right. The period cell did not have protective barriers, although they agree that this class can be avoided by considering the current. We should focus a little on this and then not the maintenance of the solution. 100%. There was some very minor protection. There was some fender system there, and it wasn't sufficient enough. But everything else, I couldn't agree more. William, with you.
Mm-hmm.
Uh,
We also have Richard here.
and Richard Hobart Bridge, Barker hit the pans. I will check it. Interesting.
Mm-hmm.
Interesting. Yeah, well, this here, this Prasanna. The overall, there was some statistics here which I can actually find quite easy for you. How many vessel collisions happening every year? Not only major ones, and not only in US and Australia. So I
Mm-hmm.
can actually, if you give me 1 second, I will probably find it in the number just out of curiosity. This one. What's this? For the last 50 years, 35 major bridge collapses due to ship barge collision. 35 major ones of the scale of the one we've discussed. Right. So fortunately, I don't know all of them. I apologize. I'm sorry. The Shingon floating bridge, but I will definitely, I will take a look.
Mhm.
Having a bridge across the.
So, Dr. Igor, we also have, let's have this from Sharfuddin. I think this will be our last question for the day. Um, he wanted to, you said that this particular bridge could not have been saved. It is normed that this bridge was designed for that time period, 1977 of ships, and carrying capacity with the time the ship sizes. DL could significantly increase. It is now road authorities to consider and strengthen and take upgrades based on the risk and mitigate risk. So it's not a question, but it's sharing an information. Thank you so
It
much
is
for
a
that,
statement.
Dr.
I agree 100%. Agree. That's probably one of my main points over here.
Mm-hmm,
So all this procedure of risk analysis and this
mm-hmm,
allows you to come up
mm-hmm,
with the better idea. So once you've got this idea, you can build this risk assessment and you can tell
mm-hmm,
which structural system, not only particular pier or particular kind of a pillar or abutment, but the
mm-hmm,
structural system you will pick. Well, I'm fairly sure the truss bridges would not be built there because their risk is too high. And we see many cases, like many cases, two, three is already many for this type of structures. And I agree 100% for the considerations, for the current considerations, all these risk assessment procedures needs to be used, and they will probably be used for the new structures.
mm-hmm,
Like I said, the current problem is what to do, what we should do with the existing structures. That's the main problem. But new structures, new bridges, well, and even the question if the bridge across Cook Strait is possible, well, it is. The bridges you can see built like in the far east of Russia, the Rusky Bridge, oh, it's probably about the same length. So it is possible. Underwater tunnels, so well, I think it's more underground structures, so will be more complicated in this case. Underground, underwater structures.
So, all right. I think there's no more question, Dr. Igor.
No,
So, yep.
I don't. No, I don't see. I don't see anything actually.
Yeah. Yeah.
No, I don't see. Well, the Cook
Mm-hmm,
Strait Bridge, I stated my opinion, and the Hobart. I'm actually writing down all this. I want to have a look at this.
mm-hmm.
Yeah, I will definitely thank you for bringing it up. Interesting cases are always interesting.
Yes, that's true.
Uh,
Mm-hmm. So, yep. There are any more questions, everyone? All right. So, yeah, let me share my screen. All right. Dr. Igor, thank you so much again for sharing this very informative session. Thank you for letting us understand what happened. And then, yep, any further questions, you can actually send that one. I still have a few minutes, and then we will answer that one for you. Okay. And then just reminder, guys, you need to request for your certificates. So you can see on your screen the link and then the QR code. Okay. All right. Mhm.
Right.
All right. Thank you
Okay.
so much, everyone. Thank you for attending our webinar today, and then hope to see you soon in the future webinars. Thank you so much. Have a good day.
See ya.
Mhm.